Hello students, welcome to the 20th lecture on particle physics, and today we are going to discuss a topic which is known by the name G-parity. We have discussed parity, we have discussed C-parity. Now today I am going to talk about G-parity. Now we have seen that when we talk about C-parity, then pi plus, pi minus states, they are not good eigenstates, because when C operates on this we get a pi minus, or C operate on this we get say pi plus. And we have also seen that when C operates on proton we get an antiproton. Therefore these were the cases where these C's are not the good eigenst. These states are not good eigenstates for the charge conjugation operation. What we saw that we have pi 0, omega 0, phi 0 as the particles which are good C eigenstates. Now for the mesons, to include all the three pions like pi plus, pi 0 and pi minus, rho plus, rho 0 and rho minus, etc., we define G-parity. And the quantum number associated with the G-parity operator is the conserved quantum number in the case of a strong interaction, while it gets violated in weak and electromagnetic interactions. Therefore, in the case of pion triplet, pi 0 is a definite C-parity eigenstate, while pi plus and pi minus are not. Since the strong interaction does not distinguish among pi plus, pi 0 and pi minus, because as we switch off the electromagnetic interaction, it is impossible to distinguish among pi plus, pi minus and pi 0. In view of this, the concept of G-parity was introduced by Li and Yang to the multiplets of mesons which have strangeness, charmness, bottomness equal to 0. Let me repeat it. Strangeness, charmness, bottomness equal to 0 for those mesons. And G-parity operator is defined as the product of the charge conjugation and rotation in the isotopic spin space by 180 degrees around y-axis. That means this is defined as charge conjugation operation and the rotation around y-axis by 180 degree in the isotopic spin space. The strong interaction is invariant under both charge conjugation operation as well as isospin. Therefore, strong interaction is invariant under G-parity. While the weak and electromagnetic interactions do not conserve isospin. Remember, when we are talking about isotopic spin, we discussed that I is violated in weak interaction as well as I is violated in electromagnetic interaction. Therefore, weak and electromagnetic interactions are not invariant under G-parity. Now, what's the G-parity of pions? In the isospin coordinate system, the components of the pion field form an isovector, where pi is expressed as having components like pi x, pi y, and pi z. And then the charged and neutral pions, they are expressed in terms of pi plus as 1 by root 2 pi x plus I pi y, pi minus as 1 by root 2 pi x minus I pi y, and pi 0 is equal to pi z. Equivalently, I can write pi x as 1 by root 2 pi plus plus pi minus, as you can have root 2 pi plus is equal to pi x plus I pi y, and root 2 pi minus as pi x minus I pi y you add them, you have pi x is equal to 1 by root 2 pi plus pi minus, and similarly when you will subtract it, this will be pi y is equal to minus I by root 2 pi plus minus pi minus, and pi z is the same as pi 0. Now when we are talking about the rotation in isotopic spin space along y-axis by 180 degrees, then what it will do, it will change pi x to minus pi x, pi z to minus pi z without changing pi y, because it is rotation around y-axis, and therefore this rotation will give us pi x to minus pi x, pi y will remain unchanged, and pi z will change to minus pi z. And therefore if you go back, you can write, you see here, you have pi x as 1 by root 2 pi plus pi minus, or pi plus minus is 1 by root 2 pi x plus minus I pi y. You see that pi z changes sign. Therefore, pi 0 is changing sign. Here in this case, you notice pi x is changing sign, y is not changing sign. Therefore, 1 by root 2, this is becoming minus pi x, this is I pi y, and that means this is equal to 1 by root 2. If I take minus sign common, this will be pi x minus I pi y. And when this is pi x minus I pi y by root 2, this is nothing but pi minus. Therefore, this is minus pi minus. That is what here we have written. Pi plus minus 0 is minus pi minus plus 0 under isotopic spin rotation. Now, let us talk about pi plus minus. What happens when we operate by charge conjugation operation? When we operate by charge conjugation operation, pi plus changes to pi minus, or pi minus changes to pi plus, while pi 0 remains unchanged. Now, which implies that, notice, what is my pi x? 1 by root 2 pi plus pi minus. Therefore, my pi x is 1 by root 2 pi plus pi minus. And that means pi plus is becoming pi minus, and pi minus is becoming pi plus, and therefore there is no change, and therefore pi x under charge conjugation remains pi x. While pi y is 1 by root 2 pi plus minus pi minus. Minus 1 by root 2 pi plus minus pi minus I by root 2 pi plus minus pi minus. If I am operating by C, then pi minus, this will become minus, this will become plus, and when I will take it the sign out, we will overall a negative sign. Therefore, pi y is giving us minus pi y, while pi z will remain unchanged. Therefore, under charge conjugation, pi x is remains as pi x, pi z remains as pi z, but pi y changes to minus pi y. While if you take isotopic spin rotation along y-axis, all three of them have minus sign. Therefore, if I put all three together, then what you notice, that under G-parity, which is C to the power I pi Iy, C, you notice here pi x, C does not change sign, but because of this guy, you have a minus sign. Pi y, because of C, there is a change of sign. There is no change of sign because rotation is along the y-axis. And for pi z, there is a change of sign because of this guy. There is no change of sign because of C. But what you notice, that under G, all of them are changing sign. And therefore, what you have, pi plus minus under G is giving you minus pi plus minus, while pi 0 is giving you minus pi 0. Therefore, one may observe that charge as well as neutral pions are a definite eigenstate of G with eigenvalue minus 1. And therefore, the G parity of isotriplet of pion is minus 1. And that is why I have written it in as an isotriplet state, and here minus 1 is showing the eigenvalue. Therefore, G parity of the pions, they are minus 1. Similarly, if we have n number of pions in the final state, because G parity is also a multiplicative quantum number, then we can write it as minus 1 to the power n, n pi. This is important. Notice here, this is minus 1 to the power n, n pi. Now, for example, rho meson has the eigenvalue of G parity, G is equal to plus 1. Therefore, it should only decay to even number of pions. As you can notice, 2 pions means the eigenvalue will be plus 1. G is even, therefore G should decay into 2 pions. Rho should decay into 2 pions, either pi plus pi minus or pi 0 pi 0. It decays to pi plus pi minus. It does not decay to pi 0 pi 0. That is for the another reason that we will discuss in the class. This is related with symmetry of the states. While this rho decaying into pi plus pi minus is a strong process, therefore what has been observed that rho decays to 2 pions, while rho does not decay to 3 pions, because 3 pions means parity, G parity for 1 pion is negative. This will be overall negative, while this is plus 1. G parity of rho meson is plus 1. Therefore, this is violating G parity, while G parity is conserved in strong interactions. Therefore, this we observe in nature, rho decaying into 2 pions, rho decaying to 3 pions has not been observed. Similarly, omega meson has G parity minus 1, and it has been found out that omega meson decays to 3 pions while it does not decay to 2 pions, because 3 pions will give us G parity minus eigenvalue minus 1, while 2 pions will give me plus 1. Because of the G parity, similarly, this is the same reason for phi meson, psi meson, etc. That phi meson, psi mesons, all of them do decay to 3 pions and they do not decay into 2 pions, because D parity of all these mesons, phi, psi, etc. like omega, they have eigenvalue minus 1, while rho has the eigenvalue plus 1, and we have seen that pion has also eigenvalue minus 1. So therefore, G parity is conserved in strong interaction processes, while it gets violated in electromagnetic and weak interaction processes. Now with this, let us come to the combined CP operation. What we have seen that we have charge conjugation operation, we have parity operation. What happens when we take both of them together? Now, CP is a conservation law which holds good in the case of strong interaction as well as in electromagnetic interaction processes, while it gets violated in the weak interaction process. But we will start with a simple example which is interesting, and then we will talk in the next class about the pion regeneration and CP violation. Now, if I talk about a pion decaying into muon plus neutrino, then what I had told you that neutrinos are left-handed particles And because neutrinos are left-handed, mu plus here also in the decay of pi plus at rest will be a left-handed mu plus. Now what happens when we operate a charge conjugation by the charge conjugation operation? Then pi plus will become pi minus, nu mu will become nu mu bar, and mu plus will become mu minus without changing its spin, without changing its momentum. But doing so, what we realize that this nu mu bar has become left-handed, which has not been observed. Therefore, directly you can see that this process, which has been shown here on the bottom left, has not been observed. Similarly, if we talk about applying here the parity operation, then parity is an operation of spatial inversion. It changes P2 minus P without changing its angular momenta, without changing the particles, and therefore pi plus nu mu and mu plus will remain as it is, and therefore only what is going to change? The momenta is going to change. That means mu plus, which was initially being emitted in the downward direction, now say it is getting emitted in the forward direction without changing its angular momenta. Therefore, here what has been observed, that nu mu is becoming right-handed, and this process has not been observed in nature. When we take both of them CP together, then as this is equivalent to operating by C and then operating by P. Once we have operated by C and then we are operating by P, therefore what P is doing, P is changing the spatial coordinates, changing R2 minus R, momentum 2 minus P, etc. Therefore, now mu minus will be getting emitted in the upward direction and nu mu bar will be emitted in the downward direction without changing the spin. Therefore, you can see that mu minus is getting emitted in the upward direction without changing the spin, and nu mu bar is getting emitted in the downward direction without changing its spin. Now mu minus has become right-handed and nu mu bar has become right-handed. Now nu mu bar, we know that is a right-handed neutrino, and this has been observed by nature. Similarly, if you can see here, when we operate by P and then we operate by C, therefore C is not going to change the momenta, C is not going to change angular momenta. So what it is going to change is it will take particle to an anti-particle state, mu plus, mu minus, pi plus, pi minus, nu mu to nu mu bar, and what we are discussing is that this process has been observed. Therefore, it is whether you are talking about CP or PC, that is one and the same. And this is an example where it looks that in weak interaction CP is conserved. But in neutral Keon oscillation, or in the B0 meson oscillation, or in the D0 meson oscillation, where you have K0 propagating in space, or B0 meson is propagating in space, or D0 meson is propagating in space, then what we will see that we have started with a K0 beam and we are finding an event where we have a K0, where that event is possible only when there is a K0 bar. And this is known as Keon regeneration. You have beam of K0 and then you are finding a few events which are only possible when you will have a K0 bar. And similarly, you start with a K0 beam and then after some time you are finding that as the K0 bar is traveling in space and time, then you have some event that is only possible if a K0 is present. And then that is known by the name Keon regeneration. And that means K0 bar are the production states. They are produced with a definite mass. But when they propagate in space, they propagate as an admixture of K10 and K20. Or simply you can say that K1 and K2. When this admixture which travels in space with time, we say that the oscillation probability of K0 and K0 bar that changes. We have certain numbers of K0 bar, or in other case we have certain number of K0. This is known as Keon regeneration. What we will see that this K0 and K0 bar, they are not CP eigenstates. We will try to form definite CP eigenstates, and then we will talk about the CP violation in the neutral Keon sector. That will also can be also applied to D0, D0 bar meson sectors. That can be applied to B0 bar, B0 bar meson sectors. Therefore, let us stop here. We will start from this point when we will discuss about the CP violation in the neutral Keon sector. Thank you very much.